Hi everyone. So we're rotating this region of sine around the line y equals 1. Goink. And we're doing it with shells this time. So when I think about shells, I always think about drawing a segment that's parallel to the axis of rotation. And at the ends of that segment, I draw my circles whose center is the axis of rotation. Now, I know that if there's an ordered pair here, we can call it xy, where this distance is y. This distance is 1. So my radius must be 1 minus y. But wait a minute. Is this a dx or a dy shape? Well, the thickness of that layer is vertical. And so it's going to be measured over here on the y-axis. So I do want this in terms of y. That's really good. Now, what about the height? Well, the height is here. This distance is x. And this distance is pi over 2. So if we take our pi over 2 and take our x value away, we'll be left with the height. Pi over 2 minus x. You know, this is going to be a dy integral, and so we're going to need to have this x gone, and we need to replace this with what x is equal to. So remember, we have y equals sine x, and we're going to take the inverse sine of both sides, and we'll end up with sine inverse y equals x. So I can say then that height is pi over 2 minus sine inverse y. Excellent. Okay. So my integral is going to be 2 pi 1 minus y pi over 2 minus sine inverse of y dy. And since we're talking dy, we want to integrate from this y value to this y value. All right. What's next? Well, that was 8, so 9. 9 is that situation where we're spinning about x equals 3 pi over 4. Here's pi over 2. So 3 pi over 4 must be over here. And if we're thinking about doing washers, we're going to be drawing something that is perpendicular to the axis of rotation, because we're rotating around this. And at each end of that segment, I'm drawing a circle whose center is the axis of rotation. Well, the thickness of that layer is going to be a vertical thing. And so I'm going to be measuring that over here as a dy. Okay, so this is a dy for number 9. I guess that tells us we know that 10 is going to be a dx. Now, if I were setting up this integral, I'd want to know little r and big R. Well, little r is this distance, and I notice that whether I draw here, or here, or here, that little r is always the same. It's always 3 pi over 4 minus pi over 2 for pi over 4. That's our little r. Our big R is a little more challenging. We know there's an ordered pair here called xy. This distance is y. This distance is x. Here, I have 3 pi over 4. Here I have x. My big R is this length. It's 3 pi over 4. Take this piece away. to be left with big R. Big R is 3 pi over 4 minus x. Oh, but remember, this is a dy integral, and so we're going to have to get rid of this x and replace that x with what x is equal to. And then we did that in problem 8, and we realized that this would be sine inverse of y. Okay, so my integral then, what does the integral look like? The integral is going to be pi, big R, 3 pi over 4 minus sine inverse of y squared minus pi over 4 squared dy. And from where to where? Well, we're integrating from this y value to this y value, so that's 0 to 1. That looks like one of the most horrible things I've ever, I would never want to do that by hand. Thank you, trusty calculator, for being my friend in such horrible situations. So let's take care of this last one, number 10. 10 says we're still going to rotate around 3 pi over 4, but this time we're going to use shells. So I draw something parallel to the axis of rotation, and at each end of that segment I draw a circle whose center is the axis of rotation. Okay, so there's my shell. Here's my radius, and we know that this distance is 3 pi over 4, and we know that this distance is x. So our radius, what's our radius going to be? I agree, it should be 3 pi over 4 minus x. And since the thickness of this shell, look, there it is, it's a horizontal thickness, it's going to be measured on the x-axis. It's a dx integral. The only thing I still need is the height, and it looks like the height here is my y value at that ordered pair. Okay, height equals y, but since we're looking for a dx thing here, what's y equal to? Well, just sine x. So my integral will be, remember, we're not integrating all the way to here. We're just integrating the region. We're going to go from 0 to pi over 2. And this is shells, so 2 pi, 3 pi over 4 minus x times the height of sine x dx. All right, so that's those. Okay, and now we're supposed to, I think we've just done these, and that we need to do these now. Sketch the situations and determine each of those. I kind of did that in these last couple, but since this is the second video, I don't know. Was it done here already? Well, I'll go through them quickly, and feel free to skip if you need to skip ahead. Let's have some sort of symbol when I get to the next part. The next part is the matching part. Okay, I'll try and remember to draw this in the corner. So once you see that, you know we've gotten to the matching part. Okay, number 1, region spun around the y-axis. We're taking this region, we're spinning it around the y-axis. We know that there's a point called xy. So our inner radius here is our x value. Now remember, this is a dy integral, and so we need sine inverse of y. Okay, and big R, what's big R? Well, big R is from here to there, from here to there. Big R is in fact a constant pi over 2. So we're doing dy, so we're integrating from 0 to 1, And we want pi sine inverse of y squared dy. Okay, 2. What's number 2 going to be? 2 is the same thing but shells. Okay. Parallel to the axis of rotation. I see that my height is my y value, and my radius is my x value. This is a dx integral. See that horizontal thickness that would have to be measured on the x-axis? So we want everything in terms of x's. And so we're going to integrate them from 0 to pi over 2. And we'll want 2 pi x sine earth x dx. All right. 3. Around the x-axis. Okay. There we go, around the x-axis. This is what we're rotating about. So I draw something that is perpendicular to the axis of rotation. And I notice that since my region actually sits along that axis, instead of having a big R and a little r, I just have a little r here. So what's my little r? Well, my little r is that y value, right? Because this is x and this is y. And I just want to say, all those years your elementary school, no, middle school teacher was talking to you about ordered pairs, and you said, yeah, I got it, I understand. They were getting you ready for this. So this overness, this upness, yep. So our radius is our x value, and that's great because we know this is a dx thickness. Okay, and we're just going to do 0 to pi over 2 pi radius squared dx. Oh, that's so gentle. Okay, what if we do this problem instead with shells? Okay, we're going around the x-axis. We draw something that's parallel to the axis of rotation, and at each end of that segment we make a circle whose center is the axis of rotation. Fabulous. Over here there's this point called xy. I know this amount is x, and this amount, oh, that's the radius. Radius is y. Good. Now, what about the height? Well, I know that this distance is pi over 2, and this distance is x. So my height is going to be pi over 2 minus x. But it's a dy thickness. That's a vertical thickness, and so we need to get rid of this x and replace that x with what x is equal to. And we know that's sine inverse of y. So my integral here, 2 pi y times pi over 2 minus sine inverse of y dy. And since I'm doing y's, I'm going 0 to 1. Okay? All right, that's 4. About 5. 5, we're spinning around pi over 2. Okay. So we've got our region, here's pi over 2, this is what we're rotating around. And the first time, of course, we're doing disks and washers. Since my region has no gap between the axis and rotation and the region itself, I know there's only going to be a disk here, so we only need a little r. Again, this is called xy. This amount is x, this amount is y. We need this amount. This is pi over 2, this is x, and so our radius must be pi over 2 minus x. Since the thickness of this would be measured, it's a vertical thickness, would be measured as a dy, we have to get rid of that x, pi over 2 minus sine inverse of y. Okay, so my integral We're doing y's here, so we're going 0 to 1. And we want pi radius dy. No, I really don't want to do that by hand, ever. I like to think I made it to retirement without ever having to do something like that by hand. You should too. And then the next one is, so we're going to take that region, we're going to rotate around x equals pi over 2, but this time we're going to be using shells. So I draw something parallel to the axis of rotation, and at each end of that segment that I've drawn, I make a circle whose center is the axis of rotation. Okay, that's our y value. This is our x value. This is pi over 2. So our radius should be pi over 2 minus x. And our height is y, also known as sine x. Remember, we talked about this being a horizontal thickness, so we've got a dx thickness here. So we want everything in terms of x's. Since we're using x's, we want to go with x bounds from 0 to pi over 2. 2 pi over 2 minus x sine x dx. Okay, so that was 6. What about 7? Now we're rotating around y equals 1. Okay, there's our region. Here's y equals 1. We're using discs and washers, so I draw something that's perpendicular to the axis of rotation. And at each end of that segment, I draw a circle whose center is the axis of rotation. Now, at this ordered pair, that is the y value, and that distance is 1. So what's little r? Little r is going to be 1 minus y. However, this thickness is a horizontal thickness, so I need x stuff here. Okay. Now what about big R? Well, regardless of where I draw this shape, big R is a constant. It's 1 minus 0 to get this length, 1 minus 0 or 1. So our integral then will be integral, and we're doing x's, so we want 0 to pi over 2 of pi, I guess I should put the pi out in front, and then just have 1 squared minus 1 minus sine x squared dx. All right, what about using shells for this situation? Okay, so I've got this, I've got this, I'm rotating about this, y equals 1. And I'm doing shells, so I draw something parallel to the axis of rotation. At each end of that segment, I draw a circle whose center is the axis of rotation. This distance is y. This distance is 1. So our radius is 1 minus y. This is a dy integral. See how that thickness is vertical? So that's good, but we still need to find h. What can we say about h here? H is going to be this. Well, we know that this is called x, and this is pi over 2, so this must be pi over 2 minus x. But since this is a dy integral, we've got to get rid of that and put in sine inverse of y. So my integral here will be from 0 to 1 of 2 pi 1 minus y times pi over 2 minus sine inverse of y dy. Ta-da! Okay, And then we're now spinning around 3 pi over 4. Okay, let's see about these. 3 pi over 4 looks like that. Okay, and that's what I'm spinning around with discs and washers. I draw something perpendicular, and I make, there we go, circles at each end of that segment whose center is the axis of rotation. Now, what can we see about little r here? Little r is this distance. And I notice that wherever I choose to draw that segment, my little r is staying the same length. Little r is 3 pi over 4 minus pi over 2. So we get a little r of pi over 4. Big R is a little more challenging. It's not a constant. We know if we have this ordered pair here, this distance is x. This distance is 3 pi over 4. And so our big radius is going to be 3 pi over 4 minus x. However, this is a dy thickness, so I know that's got to be 3 pi over 4 minus sine inverse of y. That's constant, so my integral then, remember we're only integrating the region. So even though we're rotating around this, it's dy, okay. We're still just going 0 to 1. We have pi, big R, 3 pi over 4 minus sine inverse of y squared minus little r, 3 pi over 4, oops, pi over 4 squared dy. Okay, so that's that one. Excellent. And then the last one, let's see if we can get that here. Rotating around this, we want to draw something parallel to the axis of rotation. Now, our ordered pair here tells me that this is x, and that this is 3 pi over 4. So my radius must be 3 pi over 4 minus x. Okay. Is this dx or dy? Well, I see the thickness down here as being a horizontal thickness, and so I know this is a dx integral, and therefore this is great. All I need now is the height, and the height is this y value. But since we're doing dx, we'll want sine x. So my integral of 2 pi, 3 pi over 4 minus x times sine x dx. And again, we're integrating this region. We are not integrating out to 3 pi over 4. Yes, we're rotating around that, but our integrated region stops at pi over 2. So this is just 0 to pi over 2. Okay? Pay attention to that. That's a place where students often make mistakes. Okay, so matching. So A was number 7, and B was number 6, and C was number 4, and D, this is us spinning around the the y-axis. So for D, we've got number 1. E is number 5. F is 8. I just saw that one a moment ago. G, well, this must be 2, right? Because that's us spinning around the y-axis again. H is number 3. I is the one we just did, and this is number 10. And the one that's not shown is number 9. Then I've already drawn number 9 for you, so you should be able to draw that now yourself. Okay? All right, well, no, really. I mean, I think if you can do these setups, you're good to go. And anything that seemed like it would be horrible to integrate by hand, yeah, no one's going to ask you to integrate anything horrible by hand. It's going to be a calculator question, so make sure you can type some of those into your calculator. Okie doke. All right. Yeah, this I think was a very useful practice opportunity, and I say huzzah to you. All right. Do you think we need some more? I got some more if you want to do some more. Sure, let's do some more. So how about this? If you feel like you need some more, stick around. Let's take a look at a new region. Our new region is going to be y equals ln of x on 1 to e. Okay? All right. So, let's do our thing. Let's rotate about the x-axis. Okay? So, and, washer or disk, I'll let you tell me which it's going to be, versus shell. So, want to try it? Go on, go try it. And remember, it's about the x-axis. All right, just setups. Yeah. Hey, so how'd it go? Did you draw something perpendicular? Did you find out that this was going to be a dx disk whose radius is our y value here? But since this is dx, we need ln of x. So we're integrating pi from 1 to e ln of x squared dx. Excellent. And what happens if we do this with shells? Okay, so with shells, and I'm still rotating about the x-axis, I want to draw something that's parallel to the x-axis. And I notice that my radius is my y value. R equals y. And the height here, well, this distance is e. And this distance is x. So the height is going to be e minus x. Except this is a dy integral, so I've got to get rid of that. Well, I know that y equals ln of x, and I want to get x by itself. So let's exponentiate. E to the y equals x. So then my height will be e minus e to the y. We're integrating from here to here. What's this y value at e? The ln of e is 1, so we're going from 0 to 1. 0 to 1, 2 pi. Our radius was y. Our height was e minus e to the y dy. Okay. How about around the y-axis? What'll that look like? We're still taking that region from 1 to e. This time we're rotating around the y-axis. If I'm doing a disk or washer, my region is nowhere near that axis of rotation. So I know this is going to be some sort of washer. There's my segment perpendicular to the axis of rotation. And here I see that if there's an ordered pair here called xy, this distance is x. Fabulous. So little radius is x. However, the thickness of this washer, is going to be vertical, and so we know we have a dy, which means I can't have an x here. So we solved for x a moment ago and said that x was equal to e to the y. Cool. Now what can we say about big R? Look what big R is. Big R is this constant. No matter where I choose to draw, I always get the same outer radius. This is going to form a cylinder on the outside with this sort of curvy funnel-like shape on the inside. Big R is a constant E. So my pi e squared minus e to the y, don't forget squared dy. And it's dy, so we're going from 0 to 1. Okay? If you were doing this as shells, from 1 to e, you draw something that's parallel to that axis of rotation. Okay, there's my little radius. It's my x value. Oh, and my height is the y value. It's a dx thickness, a horizontal thickness, so dx integral, which means that I can't just have y here. I'm going to need y equals ln of x. So my integral will go from, remember, we're not going from 0 to e. We're just integrating the region. So we're going from 1 to e of 2 pi, the radius is x, and the height is ln of x dx. This, sure, you should be able to do that by hand. This, you should be able to do by hand. But some of those others that we saw, oh my goodness, no. No, no, no. All right, I wish you were here with me so you could tell me what you want to rotate around next. But I think I'm going to go for I'm just going to go right to the more challenging ones. So if we take our region from 1 to e, but instead I want to rotate around x equals 2e. All right. So if I do disks and washers, I want something that is perpendicular to that axis of rotation. And look at that distance. That's the distance from here to here. Now, if I were to draw that someplace else, like down here, well, look, it's the same little r. Little r is simply the distance from here to here, 2e minus e, so r is e. All right, now what about big R? Big R, that's bigger. This is x. This is 2e. So big R is 2e minus x. However, the thickness here is a vertical thickness. And because this is a vertical thickness, we have a dy integral, so no x here. We're going to need 2e minus e to the y. And so my integral can then be integral from 0 to 1, because we're going this way, 2 pi, no, this is not shells, this is washer, pi, big R, 2e minus e to the y, squared, minus little r, e squared dy. And what about doing this with shells? Okay, so here we are, rotating around this, e to e1. And since we're doing shells, we want something that is parallel to the axis of rotation. Okay, so what can you say about radius? Well, this distance is 2e, and this distance is x. So little r is going to be 2e minus x. And that's okay because our thickness is horizontal, so we have a dx integral here. Fabulous. Now, what's the other thing we need? Well, we're going to need h. And h is the y value here. This is a dx integral, so even though h is the y value, I want to go with ln of x. So my integral, and remember we're only integrating the region from 1 to e of 2 pi 2e minus x times ln of x dx. I think you could do that by hand. I'm not going to do it right now with you by hand, but I think you could do it by hand. And then for our last one, what if we take that region and spin it around y equals negative 1? Okay? So we've got this region, this is e, this is 1, and we're rotating it around y equals negative 1. Okay, so if I'm doing disks and washers, I'm drawing something perpendicular to the axis of rotation, and that's going to be my little r. And what I know about that is, if I draw that here, I'm going to have the same amount, right? If I draw it here, yep, same. So I see my little r as being a constant. Okay, what is that constant? Well, top minus bottom. 0 minus a minus 1 equals 1. So little r is 1. Okay, what about big R? All right, well, let's get a different color here. This is my y value, and this is 1. So I know that big R is y plus 1. You could also understand this as top minus bottom, and so you get y plus 1. Is this a dx or a dy integral? Well, the thickness of this is horizontal. We're going to be measuring this on the x-axis. So I have to get rid of that y and replace it with some x stuff. And that plus 1. Okay, so we're going to integrate from 1 to e pi big R minus little r dx. Nice. And then finally, let's see if we can do this with shells. So I want to, still around y equals negative 1, I want to draw something parallel to the axis of rotation. Okay, and so what can we say about radius? Radius is this. Well, that's my y value, and that's 1. So again, we could do y minus a minus 1 and get y plus 1. And we like y plus 1 because the thickness of this shell is vertical thickness, and so we know we have a dy integral. And this is radius. What about height? Here's our height. That's h. This is x. This is pi over 2. So height is going to be pi over 2 minus x, but it's a dy integral. So we need pi over 2 minus e to the y. So our integral 2 pi radius y plus 1 times our height pi over 2 minus e to the y dy. What about our integration bounds? We're going from here to here, so we're going 0 to 1. Alrighty. I think that's, if you can do these, you don't need day 6. No, really. I think, you should be able to do these. Doing these is good. Doing these faster, even better. Anything else today? No, that's it. I think in the next one, maybe it'll be a good time for us to do some practice AP questions. Okay? We'll do that next time. Have a great day, everyone.